A rate law simply tells you how the rate of reaction changes as reacting concentrations change. Sometimes a more useful mathematical relationship will be one that shows how the reacting concentration changes over a period of time. Sometimes it's more important to know the relationship between concentration and time rather than concentration versus rate. Sometimes you want to know how much is left after a period of time. That would be more useful to you than knowing the rate that it's being consumed. Basically, after 10 minutes, how much is still present of the substance? 50%, 60%, etc. Using calculus, we can transform a rate law into a mathematical relationship between concentration and time. We refer to this as the integrated rate equation. This provides a graphical method for determining rate laws. We can look at the graph and determine if it's a zero order, a first order, or a second order, etc. We will start with the first order integrated rate equation, but there are other ones that we will learn as well. We'll also learn the zero and the second order. Depending on the order of the reaction, there will be a different equation. For these integrated rate equations, we're going to concentrate on a simple case. Case where we have one reactant with a coefficient of 1 going to products. You may recall that for the rate, it's the change in concentration over change in time. Okay? Or a rate of a first order rate equation, it would be K times the concentration of A to the first power. We can take this rate equation, do some calculus, and end up with what we refer to as the integrated rate equation. Using calculus, we get to the following equation, which is your natural log of the concentration of A subscript T divided by the concentration of A subscript 0, which is equal to a negative KT. The concentration of A subscript T is the concentration of reactant A at time T. Concentration of A at subscript 0 is your initial concentration. The ratio of concentration of time at time T to time initial is that fraction of A remaining at time T. This becomes important when we start talking about nuclear chemistry, which we refer to later on, but it's not as important in this topic that we're covering right now. This equation allows you to calculate the concentration of A at any time T, or vice versa. If I have time, I can calculate concentration. Now, to help you remember the equations, because I'm going to give you three, okay, the zero, the first, and the second, we're going to place the equation in a more useful form that makes it easier to remember. If you go back to our original equation, natural log of AT over A0 is equal to negative KT. By definition of logs, when one species is divided by the other in logs, we basically can subtract them and still be equivalent to the same value. So the expression natural log of AT over A0 is equivalent to the same thing as going natural log of AT minus natural log of A0. Now what we're going to do is now put this equation in the format that you may be familiar with, which is your y is equal to mx plus b format. That is your equation of a line, where on the y-axis you have your y values, along the horizontal axis you have your x values, and you have a slope of a line which is equivalent to m. Okay? Where b is where it intersects that y-axis is where b is. Okay? Where it intersects that y-axis. So we're going to do the same thing with this equation. So I'm going to bring my natural log of A0 to the other side. Okay, when I do that, I come up with the equation natural log of AT is equal to a negative KT plus the natural log of A0. This is the equation that we want to memorize as our first order integrated equation. Okay, this is the one that we're going to memorize. It's in the y equals mx plus b format. I'm going to give you the other two equations in a similar format, and you're going to see the differences that allows you to memorize them a little easier. With this equation, we now can draw a graph, and on the y-axis, we will plot natural log of your concentration of AT. On the x-axis, we will plot T. And since it has a negative slope, then the line will go down to the ground. The slope of that line will be equal to a negative K. The importance of this graph is that if we plot our data, natural log of A versus time, and we get a linear line, a straight line, then it is that order. Okay? If we plot our data of natural log of A versus time, and we get a curved line, it is not first order. Okay? If it is a linear line, it is first order. If we get a curved line, it is not a first order. I'm going to give you the zero, the first, and the second order equations, and if you do the plots of your y equals mx plus b, only one of them will be a linear line. If you get a linear line, then that is that order. The other two, if you plot the data, will not be a linear line. So it'll only be a linear line in one of the three plots. Okay, the one that we talked about so far is natural log of A versus time, which is your first order equation. Okay, but remember, it'll only be a linear line in one of them. The other two, it will be curved. That will become important when we start talking about problems, because I will give you information in a problem about the graphs and tell you that it's linear in this one, but it's not linear in the other ones, and that's allowing you to determine which order the reaction is, for you to know which equation to use. This means if you plot natural log of A versus time, you will get a straight line for the first order reaction. You will always get a straight line if the reaction is first order. Okay, if it's the first order. But you will not get a straight line if it is not first order. Okay, you plot natural log of A on the y-axis because that's your dependent variable. That's the one that we're measuring. Okay, versus time on your x-axis, which is your independent variable. That's the one you have control of. We're setting what time we're going to check the concentration of. The slope, you may recall, that's rise over run of the line, gives you the K. And in fact, it's the negative K. Okay, based that it's a negative slope on the first integrated rate equation. Now, the problem that comes in is if you're doing a plot of natural log of A at time t versus time, and you get a plot, and you know the slope is equal to negative K, the question is, what are the units on K? Okay, what are the units on K? Well, you either can memorize them, okay, is that the units of a first order equation or time minus 1, or you can figure it out. That goes back to a couple of slides ago when we talked about the units on K. You might recall that we know that K has units of molarity to the n and time minus 1. We also said that if you take the sum of your units of K, which in this case would be n minus 1, it's equal to the negative overall order of the reaction. So in this case, we're looking at n minus 1 is equal to, and we say we're talking about a first order integrated equation, so it's equal to a negative 1. 1 being the first order overall of the equation. Do the math, you get n is equal to minus 1 plus 1, which is equal to a 0. So you got molarity to the 0, time to the minus 1. Therefore, the unit is just time minus 1. As I said, you can either memorize that or figure it out through our little equation. N minus 1 is equal to the negative overall order. But there's no way to determine the K units by just looking at the slope. In lecture, you're going to have to understand this information, but we're not going to do any plots. If we were to do a plot, it looks something like this, where you would do an experiment. At different sets of time, you would measure the concentration of your N2O5 in this particular example. So at time 0, you would measure your N2O5, which is 0.0165. At 600 seconds, you would then measure it again, and you would get 0.0124. So you would continue on and get all your data. So you would measure your time versus concentration. Once you have that, now you can do different things to the data to do the different plots for your 0, your first, and second order to determine which order it is. So far, we only talked about the first order. So we will take the natural log of that concentration. So the 0.0165, take the natural log. We get a negative 4.104. We plot that versus time, which is 0, to 0 time. Next, you do the same thing for the next data point, 0.0124, take the natural log of that, you get a negative 4.390, and that's at 600 seconds. And so on and so forth, and plot the data. Then you draw your best line. Okay, you draw the best line possible between those data points. Now, sometimes it's a lot easier to see if it's a straight line by turning your paper on edge on the side and looking down the flat of the paper. That way you can see if it curves or not. Okay, but you draw the best line. If you draw it and it ends up being a straight line, then it's a first order reaction. Okay, it's linear. Okay. Now, if you were to draw your line and say the data points do not make a straight line, they tend to be more of a curved line, then it's not first order. So you're doing the plot and determine if you got a linear line or not. Now, if it's a linear line in your first order plot, then when you do your 0 order or your second order, they will not be linears. Okay? If it's linear in 0 order, then it won't be linear in first order. It's only going to be linear in one of the 3 plots. And that tells you what the order is. Okay? So there's other ways that we will do the graphs for the 0 and second order. Instead of natural log of N2O5, we will do just concentration of N2O5 for your 0 order, and we'll do the reciprocal event concentration for your second order. Let's look at a problem. This one states, the decomposition of your dinitrogen pentoxide to 2 moles of nitrogen dioxide and 0.5 moles of oxygen has a rate constant of 4.80 times 10 to the negative 4th per second. If the initial concentration of your dinitrogen pentoxide is 1.65 times 10 to the negative 2nd molarity, what is the concentration of N2O5 after 825 seconds? First question that you ask yourself about this question is, are we talking about rate versus concentration or concentration versus time? There's 2 different ways of handling this. Early in the chapter, we talked about rate versus concentration. We just recently talked about concentration versus time. So which one is it? Well, we're talking about concentration versus time. So we're talking about the integrated rate equation. The other question you got to ask yourself is, which integrated rate equation? Yes, I understand you only know one right now because I only gave you one, but eventually they're all going to be mixed up. You're going to have 0, first, and second all together, so you got to be able to look at a problem and determine which order it is so you know which equation to use. So what in this problem gives me any indication that this is a first order reaction, that we're going to use that equation, since it's the only one we know so far? Well, it goes back to that K. The information given to here tells me that the units on K is seconds minus 1. That is the units for a first order reaction. So therefore, I know it's a first order based on the units on that K, and I would use my integrated rate equation for a first order. That's one way. So you will determine by looking at the K units. That's one way. Remember, we talked about the units, so the k units will allow me to decide which order it is. Another one would just be the rate equation, right? If I say rate is equal to some constant k, and there's no a next to it because it's to the 0 power, that's a 0 order. If I was given rate is equal to some constant k, concentration of a to the first, that would be first order. Or if I was given rate is equal to some constant k, times the concentration of A to the second power, that would be a second order. Okay, so you may be given the rate law to give you an indication of which order it is. And also the other thing would be plotting information. There's different plots. If I tell you that the natural log of A times t versus time is linear, that would tell me it's a first order. Okay, and then I would tell you the other orders, your 0 and second orders, were curved. Therefore, they're not. They would have to be a first order because only one of them can be a linear one. So, we looked at the equation. We looked at the problem. We now know we use the integrated rate equation. So you got to know what that equation is and then write it out. We said it's the first order, so I have to write that equation out, which is the natural log of NT05 subscript t is equal to a negative KT plus the natural log of my N205 at time 0. So let's see if we can find this information in the problem. We're looking for the concentration of N205 at time t. Well, that's nowhere in the problem because that's what I'm given. That's what I'm trying to solve for. So I'm looking for that. Is K given in the problem? Yes, it is, right here. So I'll plug that in for K. And then I'm looking for T. Is that given? Yes, it is. The 825. That would be placed into my T. And then what is the concentration of N205 initially? That's also given to me. That is the 1.65 times 10 to the minus second molarity. That would be placed into here. I plug those numbers in. Okay, so I'll plug in my K, I'll plug in my T, and I'll plug in my concentration of N205 initially. Now, one word of caution I want to tell you here. What about the KT? One thing you might notice is that we have time units and time units. Okay, they have to cancel. That means that you have to have them the same units to cancel. So if you're given hours for one and seconds for the other, you're going to have to convert one or the other to the same units where you can cancel them out. That's someplace to look for errors. If we do the math here, 4.80 times 10 to the negative fourth times 825 is 0.396. I bring down that negative in front. And the natural log of 1.65 times 10 to the negative second is equal to a negative 4.104. Add that up, you get a negative 4.500. Now, that's not my final answer. That's the equivalent to the natural log of concentration of N205. So I got to get rid of that natural log. The way that we're going to do that is by doing the anti-log of both sides. Okay? Well, in essence, what that means is you're going to take this numeric number and put it to the e power. So when I do the anti-log, I'll lose my natural log on that side and basically take that numeric number and put it to the e power. On your calculator, do a second function natural log. That should give you an e to the x function. Or if you got a more expensive calculator, you might have to look in a table to find it. But we're trying to do an e to that value. Now let's talk about sig figs here. Okay, when you take the log of a number, say x decimal, or natural log of a number, okay, the number of sig figs, significant figures that you have in your number, okay, you have that many digits past the decimal. Okay, when you make your number. Or the opposite, that many digits past the decimal. When you do the anti-log, you get that many digits into the log. Okay, so let me show you what I mean. We plug into our calculator e to the negative 4.500. By this definition of logs, I have 1, 2, 3 digits past the decimal. So when I do the anti-log, I need that many significant figures in my answer. My answer is 0.0111, so I have 3 sig figs. Okay, so the number of digits past the decimal, I have that many sig figs in my answer. That's for the anti-log. If I do the log, the number of significant digits I have, which is 3 in this case, when I do the log of that, I would have to have 3 digits past the decimal for my value. Notice that this one, the answer is 0.0111. What should happen to the concentration of our N2O5 over time is that it should decrease. So did it decrease? Yes, it went from 0.0165 to 0.0111, which is a decrease. Here's another example. It's just like the one we just did. So first off, you got to figure out what kind of problem it is. Okay, decomposition of N2O5 to 2 NO2s and 0.502s has a rate constant of 4.80 times 10 to the negative 4th per second. It's exactly the same in the previous problem. But this time we're going to know what is the time required for the concentration of N2O5 to drop from 0.160 to 0.100 molarity. So once again, it's still concentration versus time. So we're talking integrated rate equation. We're still talking about a first order. Okay, it's still first order. So we're still using the same equation we just talked about a second ago. But in this case, we look at it, we have the concentration of our N2O5. We have that. That's our concentration at time t, which is 0.1. Okay. We have our concentration at time 0. That's our initial. We have our rate constant. Okay, all we're trying to solve for now is time. So I'm going to bring the natural log of N2O5 at time 0 to the other side. And then I'm going to plug in my values. For my time t, it's 0.1. For my time initial, it's 0.16. My k is 4.80 times 10 to the negative 4th per second. And then I'm trying to solve for time. The natural log of 0.100 is a negative 2.303. Now notice sig figs. I'm talking about 3 sig figs in my log expression. All right. So that means I need 3 digits past the decimal. And that's what I have. Okay. I'm going to subtract my natural log of my 0.16 once again. It is 3 sig figs again. Okay. So therefore, I need 3 past the decimal. That's how I'll decide my significant figures, which is a negative 1.833 in this case, equal to my k and t. Continuing on with my math, I get a negative 0.470 equal to a negative 4.80 times 10 to the negative 4th per second. Divide through still. I get a negative 0.470 divided by a negative 4.80 times 10 to the negative 4th per second. Now realize that this per second, okay, that's like saying 1 over second. So in essence, the seconds is in my numerator, which is where we want it because I'm trying to find time. And we get an answer of 979 seconds. So if I wait 979 seconds, my concentration will drop from 0.160 to 0.100 molarity. Homework number 9 deals with the integrated rate equation. Now I want to caution you that that is only about integrated rate equation of the first order. Okay, so don't get in the habit of just going through the problems, not paying attention, and just working it using the same equation. You need to analyze each question and see why you're using the first order integrated rate equation, because when it comes to the test, these are all mixed up. So you need to figure out, why am I going to pick this integrated rate equation, not the 0, not the second one, when all these become mixed up when you start studying for the tests or when it's on the test itself. Okay, that's where you're going to have to look at the units of K, if the rate law is given to you, all that information about the plots. Okay, that's where that's going to become important to determine should I use the zero, the first, or the second order equation.